Let's continue with this example. What I was saying at the end of the last video, we can't do this with every function because of the attributes of e to the x. Most importantly, that it is its own derivative. Another attribute, which we'll see later on in this lesson, is that it converges everywhere for its power series for all values of x. Because of those attributes, we can do something with e to the x that we can't do with lots of other elementary functions that we work with. E to the x is the only one that I've seen them allow you to do this on the AP exam with. So here's some things I want us to consider so that we don't have to take a long time and build a really complicated power series and eat up a lot of our valuable time. We can do some things here. I want you to realize that for e to the x, I put parentheses around the x so that you could see everywhere that there's an x in e to the x, I can, because of its special attributes, I can just feed that function on both sides. Everywhere there's an x, I'm feeding it as if it were a function machine. We talked about this early on last fall. I can feed it an x squared. And once I've fed it an x squared, we'll clean it up a little bit so you can see it a little bit easier. This is 1 plus x squared plus x to the 4th over 2 factorial plus x to the 6th over 3 factorial. Now, everywhere that function has been fed an x squared, now I'm going to feed this function everywhere that there's an x. I'm going to feed it an x minus 1. And I'm guaranteed that what's on the right-hand side here is, beyond a shadow of a doubt, because of the attributes of the function e to the x, is the correct power series for this function. So some things I want you to consider doing as time savers. This is a huge time saver on the test. And when it comes to e to the x, this is something that we can do. We'll see it in other functions as well, but it's definitely something I want you to think about doing when this function shows up. Because we can do these kinds of manipulations. If we think about inputs to function machines and corresponding outputs, we can do that in this context. All right, other mathematical operations. We are not limited to differentiation and integration. We can multiply, we can divide, we can do lots of other mathematical operations. Anything we can do as far as a mathematical operation on functions, we can do it with series as well. We have to be really meticulous about our notation. If we want to multiply these two functions, then the result on the right-hand side is going to be the product of their two power series. I would take the power series for the natural log of the quantity 1 plus x, and I would multiply it term by term with the power series expansion for the other function. Here it is e to the x. But just as in multiplying, multiple terms in any set of polynomials, we have to be really meticulous here. What I would do is I would take the first term here and multiply it by every term there. So x times 1 is x, plus x times x is x squared, plus x times x squared over 2 factorial is x cubed over 2 factorial. You definitely see what I'm doing here. So there are the first few terms. I'm not going to put a plus dot 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 yet, because now I'm going to go back and I'm going to pick up that term and multiply it by every term here. So that term multiplied by 1 gives me that. That term multiplied by x gives me that. That term multiplied by x squared over 2 factorial gives me an x to the 4th over 2 factorial, which is 2 times 2, so that's over 4. And that term multiplied by x cubed over 3 factorial will give me a minus x to the 5th over 2 times 6, which is 12. Now I'm going to come back to this term and multiply it by every term over there. And so I'm going to get an x cubed over 3, and an x to the 4th over 3, and an x to the 5th over 6, and an x to the 6th over 18. And finally, I'm going to do the same thing with the last term, which is going to give me a minus x to the 4th over 4, and a plus x to the 5th over 4, and not a plus, but a minus. Both of those are minus. Minus x to the 5th minus x to the 6th over 8, minus x to the 7th over 24. Now I'm going to put my plus dot dot dot. Now all I have left to do is some algebra. I'm going to gather like terms. Everything that just has an x term in it, and it looks like there's just that one term that's x to the power of 1. So the first term here is x. Then I'm going to gather all of my x squared terms. It looks like there's only 2. So I have one positive x squared. I'm going to take away from that half of an x squared. So that leaves me a positive 1/2 x squared. Now I'm going to do everything that is cubed. There are 3 of those. So I have positive 1/2 minus 1/2. Those two terms actually cancel. And so I'm just left with 1/3 x cubed. And then I would do anything that was x to the 4th. And there they are. So I have x to the 4th over 6 minus x to the 4th over 4 plus x to the 4th over 3 minus x to the 4th over 4. So I have, let's come out here to the side, 1/6 minus 1/4 plus 1/3 minus 1/4. So all of those have 24. 4 24ths minus 6 24ths plus 8 24ths minus another 6 24ths. So there's 12, positive 12 24ths minus 12 24ths. So the coefficient to the x to the 4th term is 0, if I did all that work right. So now let's go back and we'll get our x to the 5th terms. And there are 3 of those. So I have minus 1/12 x to the 5th, and then I have plus 1/6 x to the 5th, and then I have minus 1/4. And they all have a common denominator of 12. So 2 12ths minus 3 12ths. So those are negative 4 12ths plus 2 12ths is a negative 2 12ths, or a negative 1/6. So minus 1/6 x to the 5th. Now I could keep going, but generally we only show the first 4 non-zero terms. And now this equals the natural log of the quantity 1 plus x times e to the x. That is the power series representation for this completely new function. So lots of algebra is probably going to show up in the context of power series as well. Here's one that says divide. Well, this is polynomial, so polynomial long division. So we're going to have an entire new function that looks like this. And if we want to find what the power series representation for that is, we're going to have to do polynomial long division. It is the first function divided by the second function. Make sure you have your notation correct. 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. And again, what we would be after is we would be after finding probably about the first 4 non-zero terms. So the process for polynomial long division, I look at what's the first term that is outside here. What do I need to multiply it by to make it look like the first term inside? Well, that's x. And then I take this term and multiply it by every term that's out here. So I get x, I get x squared, I get x cubed over 2 factorial, I get x to the 4th over 4 factorial, put parentheses around it, subtract it. So just the exact same process. So now my lead terms go to 0. I have negative 1/2 x squared minus another whole x squared. So that's what that term looks like. Then I have 1/3 x cubed minus 1/2 x cubed. That's a 2/6 minus a 3/6 is a negative 1/6. So I have minus 1/6 x cubed. Then my x to the 4th terms, I have a minus 1/4 and a minus 1/24. So let's see what that will be. Minus 1/4 minus a 24th is a minus 6/24, and another 1/24 is a minus 7/24. So you see, this is just really time intensive. You're probably not going to get asked to do this in a testing situation and get asked to show much more than probably the first 2, maybe 3 non-zero terms. But I do want you to see that it's possible. Let's do one more term here. So now this is my lead term. So I look here. What do I multiply it by to make it look like that lead term? And then I take this and multiply it by every term out here. So that is a minus 3/2 x cubed, and then a minus 3/4 x to the 4th. I won't do that last term because clearly it looks like we're just going to the power of 4. But you see what I'm doing. So those first 2 terms are going to cancel. I have a minus 1/6 x cubed and a plus 3/2 x cubed. So a minus 1/6 plus 9/6 is going to give me 8/6 or 4/3. So I'm going to get 4/3 x cubed, and then so on. You get the idea. And then we could repeat the process again, multiply it here, multiply it by every term. I'm not going to take valuable time here for you to watch polynomial long division, but you get the idea, and the result, whatever we have here, is the power series representation for that function. That function is the sum of that power series. All right, so we have differentiated, integrated, multiplied, and divided. Addition and subtraction, there is expected, gather like terms. How about substitution? Could we find the power series representation for e to the sine of x through terms of degree 3? Well, let's start with the power series representation for both of the functions in question. And it says through degree 3, so there's degree 3. We need the power series representation for sine, and there they are. There's through degree 3. And then what we would need to do is we would need to plug that power series representation into the e to the x power series representation for every term, and then clean it up. I'm going to stop here. We'll pick this up in the next video.